Welcome back. I have a brief lesson for you on work and power. So work, simplistically, well, specifically by a force, is Fd cosine of theta. Fd is the key thing there. Now power is simply the rate at which that work is accomplished. So you do work, if you know the rate, it tells you the power, namely work over time. Simple as that, work over time. The unit for power, it's a joule. That's the unit for work. Standard unit for time, second. Now, a joule per second has a specific name, and that is the watt. So the watt is a joule per second. It is the standard unit for power. Now I want to massage that formula just a little bit so you can see another useful variation. Work over time. Remember, work dimensionally is force, newtons, times meters, distance. So let's just go Fd over t. So we're assuming the force and direction are the same here. And that's Fd over t. And you know what d over t is, don't you? Displacement over time, velocity. Or we'll just say speed, since we're not talking about vector quantities here. So Fv is power, the force times velocity. Here's an example then. So say we have a 7,000-pound truck developing 400 horsepower. How fast can that go up an 8% or 5-degree hill if air friction is not part of the equation? Which is very unrealistic because as a large vehicle like a truck moves down the road, air friction ends up, and other kinds of friction as well, end up being a huge factor, as we'll probably see in the result we get here. So here's the truck. Yes, listen to that diesel engine. And the velocity, or speed, going up the hill, and in the other direction, what is the force? Well, power is work over time, which is F times V. V is power over force. Just solve for V, power divided by the force. Boop, there we go. And this force is mg sine of theta. It's basically the gravitational component parallel to the inclined plane, if you remember that, and I'm sure you do. So now power is 400 horsepower. Have to convert that to standard units, namely watts, which it turns out is 746 watts per horsepower. That gives us quite a few watts. 300,000 watts. All right. Compare that to your 100-watt light bulb. Well, at this point, you probably don't have 100-watt light bulbs because you either have the fluorescent or LED types in your house, and it is a small fraction of 100 watts like they used to be typically. Anyways, let's go ahead and solve for V then. Power over force, and the only force we're considering unrealistically here is mg sine of theta. So there's the numbers. Plug that into the calculator. It gives us 107 meters per second. 107 meters per second. Convert that to miles per hour. There's the conversion. There's the result. 240 miles an hour. Yeah, that's right. Now, that is unrealistic. This 8% grade is actually, doesn't sound like much, but it's actually a fairly steep hill for standard automobiles and standard vehicles on the road. It's a lot steeper than you might think it is. It happens to be the hill that exists where I grew up in Alaska. There's a 1 mile, 8% grade hill. And back in the 70s, we used to race our vehicles up the hill, see how fast we could go over the top. I will say that my truck, which is the 7,000-pound truck that actually develops quite a bit more power than this, has got the title for the fastest vehicle over the top, at least in terms of the data that we have so far. Those of us that have actually raced to see how fast we could go. But not to divulge too much information, I do want to point out, though, that this force times velocity, this is why when you're on a bicycle when you start pedaling and go to higher gears, you can't just keep going faster and faster. To go faster and faster, you have to apply more force. And then you also, as you apply more force, you go to a faster speed. And it's the combination of these two. They're multiplied together. So the faster you go, the more force is applied to overcome friction, air resistance, whatever. And you're moving faster as well. So it's not just, it's both of these things working against you. So very quickly, when you're riding a bicycle or even an automobile, how fast can it go? And you put the pedal to the metal on a flat road, well, eventually that friction force times the velocity, which are both going up, just gets to the maximum power of the automobile engine, or the human being trying to make the bicycle go very quickly. So I want you to understand that conceptually, and that is a brief introduction to how power comes out of work.